Now we're going to deal with solving two-dimensional motion problems, just like the airplane in the wind or the boat in the river problems, except now we're going to actually look at it whenever it's in equation format. And so instead of being told the length across the river, we're going to look at equations. And the main reason you might need to do that is if the object's motion isn't following standard kinematics or standard simple ones. For example, here's a t cubed in there. Something also to notice in these equations for both the x and the y-axis is the lack of a initial starting position. These are position equations. There is no initial position there at the very beginning of all this. So whenever we're asked for displacement, we can just solve for the final position because displacement is final minus initial. If there was an initial position, we'd end up having to subtract that out. So I've got my two equations here that describe an object's position in both x and the y-axis, two-dimensional motion, and it's asking what is the displacement after 2.5 seconds. Well, after 2.5 seconds, the object will have gone a little bit in the x and some in the y, and then we've got to combine those two. So let's go about, the way you do this is you go about starting out solving this separately. So let's solve for the object's displacement in the x first. So all I need to do is rewrite the position equation and substitute in 2.5 seconds and now plug into my calculator. So I end up with a displacement of 17.5, assuming that we're in base units meters, 17.5 meters in the x-axis. Now we need to do y. All right, and so I find that in the y-axis, our new position is 11.875 meters, assuming base units. Haven't rounded for sig figs, don't do that till the very end. Now this is the exact same type of problem as the plane in the wind. I mean, this is just like in the x-axis now. The plane has traveled 17.5 meters, make that a little bit better, 7 if that's possible, 17.5 meters, while the wind is blowing it vertically up 11.8, and this is not drawn to scale quite obviously, 11.85 meters. Apologize for the poor 5 over there into the screen is giving me trouble. Now, the question is, what is the net displacement? Well, just like with the plane, I have one vector going to the right, one vector going up. Even if you look at this, this is tail to tip, meaning that I'm going to complete this triangle here. So my resultant vector is going to go just like this, r, and that is quite obviously in this right triangle because x and y, right, those are going to be at right angles to each other. Your x and your y-axis are at right angles to each other. So r, this is going to be Pythagorean theorem to get the displacement. So I come out with a displacement of 21.15 meters, but displacement is a vector, meaning that it has a direction to it. So I need to deal with angle theta here. That's the number one mistake made with vectors. Students forget to actually put a direction with it. So what angle theta, if this is if over here is 0 degrees and here's 90 degrees and here's 180 and all the way around 270, right back around 360 or 0, what angle is that? How do I figure that out? Well, inverse tangent again, because tangent of this angle is opposite divided by adjacent. And I come out with an angle of 34.16 degrees, which should make logical sense to you. The x-axis is 17.5, longer than the y-axis, 11.875, meaning that, and I'm sorry that this looks somewhat like a 3 there, that's 11, meaning that if the x-axis is bigger than the y-axis, opposite over adjacent, y over x, I should end up with an angle less than 45 degrees. If the y-axis is bigger than the x, I'll end up with something above 45 degrees here. So 34.16, round for significant figures here. Not worrying, I'm going to call the equations exact in this problem. That leaves me only 2 sig figs is what I have to deal with. So 21, and assuming base units here, 21 meters at 34 degrees. All right, B, find 2 equations that describe the object's velocity in both the x and the y-axis. Well, I have an equation for position in the x and the y-axis, and the derivative of position, or the derivative of displacement here, but the derivative of position is velocity. So we just need to take the derivatives of these 2 equations. So whenever I take the derivative in the x-axis, remember I multiply the 2 down. So I end up velocity of according to time in the x-axis, 8t minus 3. And then I end up velocity in the y-axis, 9t squared minus 14 minus 9. And that leads me to part C. Part C was, okay, what's the actual velocity of this object in two dimensions, right? Because I have both an x and a y-axis. What's the velocity of this object at 2.5 seconds? So now all I need to do is substitute in my 2.5 seconds to both the x and the y velocity equations. And I get my x and my y-axis velocities. I'm going to go ahead and use the word components because that's where we're going right now. 17, assuming base units, meters per second the x-axis, and 37.25. That's a massive number for most objects. Meters per second in the y-axis. So now I've got the two. Once again, on an x and y-axis, this is the exact same idea. If velocity was getting plotted here, I've got a 17 in the x and a 37 coming up in the y. Let's drag that vector instead of putting it right there. Let's not put it there. Let's actually instead put it tail to tip to make it even easier to see, right? So now I got 37.25 over here. So my resultant runs, tail to tip, runs from the first tail to the last tip there, r. And here's theta. So once again, for resultant velocity, I'm going to Pythagorean theorem and inverse tangent. And so I come out with these answers here, assuming base units, meters per second. Once again, two significant figures, so round off, and we have our answer.